All right, so let's go through an example of calculating the linear density for a direction. So here is our system. We are going to determine the linear density of the 0, 1, 0 direction. So it's actually the same direction we just talked about in the previous module. But in this case, we're going to do it for the FCC crystal structure. So I've drawn here the space filling version of that. And so you can use that as you calculate the 0, 1, 0. And so go through that and determine the linear density. And then what I also want you to think about is, what about the other directions in this family of directions? So answer that question as well, and then we'll come back and we'll work through this one together after you've had a chance to take a look at the quiz. All right, so I've switched over to the paper here because let's work through this problem of the linear density of the 0, 1, 0 direction, and it's in FCC. So I've resketched it here, but I've only drawn the front face, so everything else is missing. So if you want a more complete version, please go back to the slides, but I'm just going to do that. So our first step was we wanted to draw the direction. So the 0, 1, 0, we actually drew this one in the last one, right? If we see this, it means that there's only projections in the y-axis. So basically it runs along the y-axis. So basically if we pick one that's parallel to the y-axis, and for convenience, I'll just draw the front so you can see that. So starting here and then going to there. So this is my 0, 1, 0 in this cube, which is going to be FCC. All right, so that was my first step. And so now let's go ahead and work the rest of the problem, and let's do it in the order that we just talked about. So we sketched the direction, so now we're going to determine the length. And just like in the previous question, this is still a cube, even if it's FCC, it's just a different type of cube. So this direction, this length, is still A, right? So this is still equal to A. So that's going to be our length. And if we redraw it by itself, so this is our 0, 1, 0 direction, the start to the end, we see that we have basically an atom centered on the corner and another atom centered on this corner, and I try to draw them as close together as possible. So this is R, right? And then from here to here, that length is A. So from these sort of space filling models, you should already be able to tell that there's a gap space here, right? So A, it does not equal to 2R like it did in the case of the simple cube, because this is kind of expanding things out. So we know the length of the direction within the unit cell is A. So that's the second part. Now the third part is we need to calculate the number of radii along the same direction. And just like it was for simple cube, we see that we have, if we count up the r's, we got 1r here and 1r, so we're going to have 2r. So we know if we go ahead and maybe do that over here, we know that we have 2 radii, and we're going to multiply that by r, because that's going to give us the length of atom in that direction per unit cell. And then we know that the length of the direction, which is the denominator, is A, right? And so this is where the last step comes in, because we need to find that relationship between A and R so that this can be reduced, because right now this doesn't tell us much unless we have a connection between A and R. All right, so if you're asking yourself, how do we do that? Well, there's a cheat method in the book. It does give you this relationship for FCC. But again, like I said, this is something that we should be able to do. We should be able to calculate that A to R ratio for relationship for any system that we're looking at. And the way we always do that is by looking for where there's a direction that we can identify in terms of A that is also close packed, right? Where things are touching, so that we can relate A to the radius. And so if I just look at this front face, this is actually enough to tell me, right? Because I tried to reproduce this as close as possible, where there's contact here and contact here. And if you look at that, that's on the diagonal. So that's on the diagonal through the face. So we call that a face diagonal. So if we look at that face diagonal, right, we know A is this. We also know that this, because it's a cube, this length is also A. And then obviously this is a right angle. So we have a right triangle here with A, and then this is the hypotenuse, and that we could call X, like we like to do. And once we do Pythagorean theorem, we know that triangle that we're talking about, A is square root of 2A. So that's Pythagorean theorem if you want to go back and check that, is square root of 2A. So we know that the length of this in terms of A is square root of 2A. But we also know that there's contact there, here and here. So there's no empty space. And so if we count up the radii, 1, 2, 3, 4, then we know that this length is also equal to 4r, right? The same length is equal to 4r because there's no empty space. So we can say with confidence that square root of 2a is equal to 4r. And if you look in your book and you look at the relationship between a and r, this is what you'll find, and that's how they do it. So any system, you're going to look for the close contact, and then you're going to relate a and r like we did here. So that's what we're going to basically plug in to the equation up here. And so if I do that, and I choose to plug it in for a, I'm going to plug in 4r over square root of 2, because I just solved for a there. And so when I do that, and the r's are going to cancel out now, and that's the beauty of it. That's why we're doing it. So these r's cancel out. And when I put that in, I don't really like the fractions here, so I'd rather have a decimal form. That equals 7.707. So you can think of this as the fraction that is occupied by atoms on that line. So this is telling us that this line is 70.7% occupied by atoms. So this empty space is the other remaining roughly 30%, right? So we've just kind of determined the packing along a given direction. And so that, in this case, so we can call this the linear density of the 0, 1, 0. So just in subscripts there is equal to 0.707. And this is the process that we would use to do that, or to do any other combination of systems that we can think about.